shows what exactly we also do. As I mentioned, the previous one in the pictorial one, the battery module, the BMS, the battery rack and the container, the PCS and the MV station, the EMS, that is the energy management system and the hybrid controller, and obviously the installation, commissioning and operation and maintenance. So these are the basic 6 parameters of an entire typical BESS EPC, which will be very similar. Installation commissioning is common to all EPCs, operation maintenance common to all EPCs. Again, obviously the differences that I've mentioned in the first block diagram remain the same. Other than that, it is a very simple and practical thing that anybody and everybody can understand. There are obviously detailing into every aspect, but yes, we will not be getting into all those things. As you can see, obviously below are some of the points that we have done over the course of many years, and we've installed more than 11 gigawatt across the globe. So those are small points mentioned, but we can focus on the top ones for sure right now. Coming to the next slide. The important factor right now is energy storage. Now, what I tried to show you previously in the first 2-3 slides basically are electrochemical battery storage. If we go for pumped hydro, if we go for green hydrogen, the entire setup will change. So to make it very, very clear, the electrochemical battery storage is what is the most prevalent and maximum utilized. Why it is, we will come to that in the next slide. But currently, all the previous slides, this one and this one, is specifically for the electrochemical one that is being mentioned in the center. Now, again, going back to the energy storage system in itself, obviously there is a mechanical energy storage system, there is a thermal energy storage system, electrochemical, as we were talking about it, there's an electrical and chemical. Now, out of this, if you can see, we've marked and color coded a few of them. Pumped hydro has been used extensively, deployed across the globe, but fundamentally it is not feasible in all geographies or all locations. There is a major restriction on where exactly you can do it. Obviously, you need to have that availability of the river flowing and the lakes and other things. So it is a very, very location centric pumped hydro that you can go ahead with. Similarly, with compressed air and flywheel, these are very, very few and are in trial in basically the very advanced geographies such as USA, Europe kind of markets. Sorry. And green hydrogen, as color coded again, is a very upcoming and new technology, which probably see the day of light in the near future. We don't know exactly and how fast it will happen, but yes, it is changing. Technology is moving rapidly. So we can assume that green hydrogen will form a part of our system sometime or the other in the near future. Again, coming to the thermal part, we've seen these kind of molten salts where thermal energy is stored generally in the CSP plus also. Obviously not extensively used, not extensively done across the globe, and obviously not proven to be commercially very, very viable also. So not exactly moved forward on that front in too much. Going forward, we also have the electrical one. There are supercapacitors and SMES, which again are very, very advanced technologies and not commercially viable as of now. Sorry. Now coming to the main and the current part, that is electrochemical. Obviously, we've seen lead acid batteries, we've seen advanced lead acid batteries, we've seen sodium sulfur batteries. Now is the time of lithium ion batteries, and yes, there is flow batteries also. So if you see, fundamentally, what I will do is going into the next slide, you will get to know exactly what are the reasons, what are the differences, what are the solutions they offer, and what are the problems that they have. So let us go into the next slide to study more about these electrochemical batteries.
One quick comment on pumped hydro. So we in South Africa already have significant experience of pumped hydro schemes, Eskom having a few. There was actually an article yesterday to say in Switzerland they've just released a large-scale pumped hydro scheme. They didn't give the exact capacity, but they said it's up to 400,000 electric car batteries. So clearly vague enough so no one can really understand. 17 kilometers of subterranean tunnels, turbines stored at 600 meters, a price point of $2 billion. So, if you're talking that scale that Switzerland's put in place, it's a significant investment, probably out of the range of purchasability for many of the buyers on this call. Thank you.
Exactly. Exactly. Thank you. Thank you.
That's if you've got water, of course.
That's the fundamental.
Agreed.
Yeah. So do I move on to the next one?
Oh, next, please. Thank you.
Yeah. Yeah. So again, as I mentioned, we will be studying into more in-depth detail of exactly all the parameters that we look at. Now, let me just, rather than getting into all these numbers, let me just give you a quick feedback or a quick update on why exactly have lithium-ion batteries, let us say, been or started to be deployed across the globe in such a fast and a large-scale manner. There are a couple of important aspects. If you see here, the discharge time. Fundamentally, right now, although we have thermal energy or coal-based energy, or let us say some of the non-renewable sources which are controlling the grid. But with the renewable penetration into the grid, obviously you will need some kind of predictability or reliability. With excessive renewable energy into the grid, you will need more and more of that. Now, if you see that, what we need is currently, there are two aspects to it. One is how fast can it react to the changes of the load, and how long can store power and give you the give you the power output into the grid. So if you see that, there are various other uh, technologies which we can see are doing various other things, but in terms of, if you see the discharge time, it is one of the most optimum. Yes, sodium sulfur again is also optimum, but if you look at the initial capital cost of sodium sulfur or capital cost of flow batteries, that is exactly the reason why it has not got deployed so heavily. So the primary two factors of it being a commercially viable solution and does it cater to the current needs and requirements, lithium ion is the one that gives you the best possible option as of now. Technology as we speak is moving so fast, is changing so fast. Even in lithium batteries, there are so many changes, so many variants that are coming out which are trying to make it much better. Obviously we will see green hydrogen and other things also coming into play, but fundamentally the two important factors are the current need of the hour and the commercial viability of the two. So if these two factors are going to get catered, then basically that technology is going to prevail over all the other technologies. Now, if I give you a small analogy, let us say if people are more into solar or have basic knowledge of solar, let us say around 10 years ago, there was thin film technology that came into picture. And after the thin film technology, then came poly, then came mono, now it's bifacial. So why exactly has this happened? There was mono modules even when poly modules were there, but people preferred poly at that point of time because of the commercial viability and the scalability at that point of time. The moment moment the mono modules came with a better proposition and a better commercial viability, that got accepted more into the market. So fundamentally, it's more of a commercial game where if you're able to give the required necessities at a lower cost, that exactly will get accepted the fastest into the entire system. I will be sharing this slide, so obviously all the details can be gone through with you guys. If you want me to specifically run through some numbers right now, you can let me know. I will do that. Otherwise, I'll slowly move on to the next slide.
So I think let's run on to the next slide. We'll take specific questions later, but just to make a point for the benefit of the team is that initial capital cost actually looked quite low, but we do need to consider that there's a PV solution attached to this, and then this is limited to the number of hours. So we can't just take a PV $1,000 or $1 a watt and then say batteries is simplistically a third of the price. That's not the linear calculation.
So Rob,
please
I
don't
will be
infer.
answering this. I will be answering this probably of yours in the coming slides. I do have something up. So just to make people aware of the fundamental fact that yes, just because it's a $200 or $300 per kilowatt hour solution doesn't mean that that is the entire project cost. So this is only the battery cost. Fundamentally, obviously, all the other BOP and BOS put together might be increasing a little bit more, but more than that, obviously this is just a 1 hour system. So obviously if you need a 3 hour, 4 hour or 6 hour backup, accordingly you will have to size the batteries in that sense. And these batteries do degrade. So these are beginning of life sizes. At the end of life, they could be only 60% of the entire size. So depends on how you want to size it at beginning of life or end of life also. So accordingly the size also increases on that front. So I will be coming to that, Rob, probably in the next slide or so, where you might get a better picture of what exactly I will explain on that front.
Please continue. Thank you.
Okay. Not that I'm not an expert on the lithium ion battery prices as such, because there is fluctuation happening across the globe. I mean, what I can just generally do is what we have done, what we have studied, is that there are these factors that affect the cost of lithium ion batteries. Fundamentally, material cost is the most primary an important factor that has been affecting the lithium prices. If you see on the graph on the right hand side, from the lows of 2021, the lithium carbonate Li2CO3, that is industrial grade lithium carbonate, which is used to manufacture these lithium ion batteries, has approximately shot up by 800% in the last 7 to 8 months. To be very precise, from last October, November onwards. Now, the reasons for them, there are various reasons, obviously. Uh, Obviously, the entire manufacturing is specifically happening, or 95% of the manufacturing is specifically happening in China. During that time, there was a power shortage, the power cuts. There is a shortage of lithium carbonate mining in itself overall, because the same lithium batteries are getting into EV cars. So there is a huge demand for EV cars that's grown exponentially, even more than the battery energy storage system. So any cell manufacturer obviously has to choose between the two. And yes, obviously EV cars give them a better capacity than the battery energy storage system. Moving over, there was a huge logistics crisis that happened. So obviously from the mine, getting the raw material to the factories, getting it done, and then again getting it shipped. So all these have also increased the cost. But fundamentally, just to give you a small heads up, the lithium carbonate that is used to manufacture these batteries have roughly increased to around 800% in the last 9 months. In the last couple of months of these 9, there has been some stability. It has not, the prices have not fluctuated or drastically increased or decreased. So fundamentally, from whatever I've read across in the last 3-4 months, what we expect is we expect to see some stability, and we expect that the battery prices will go down to the last October 2021 numbers by 2024 only. So there's another 18 months to go until we actually see the old prices come back. Till that time, there will be stability and a slow downward trajectory, but we don't expect steep falls in the entire system. This is also due to the fact that 2024 is being mentioned because all the battery manufacturers are ramping up their capacity productions. So it's going to take them 6 to 9 months to a year to increase their manufacturing. And by that time, the manufacturing as well as the the requirement or the market requirements are going to match. So there will not be an a mismatch or a market gap that is called. So we will be able to come to a level of stability by 2024, where it will go down to the old numbers. And hopefully by that time, the lithium carbonate prices also will go down with the increase in mining and other aspects that are required. So yes, the other important aspects which hit the price are more to do towards the manufacturing processes. Every day, these electrochemical technologies are coming up with newer technologies, newer ways to cool the system, newer technologies to increase the life, increase the number of cycles. If you see, initially when we started off, there were 4,000 cycles. Now it's close to 10,000 cycles that we can expect from a lithium-ion battery, depending on number of cycles per day and depending on 20-year life cycle kind of thing. Obviously, the entire battery design is also being worked out by Koreans and Chinese all together. So what will be the separator, what will be the copper current collector, the seam, cathode, anode, everything. Obviously, even the cell format. I mean, there are 3 types mainly. There's a pouch format, there's a prismatic format, and there's a cylindrical format. So there are differences in that also. There are pluses and negatives. I mean, I'm not the right guy to discuss on those fronts. Probably a technical guy from my team will be better off. But yeah, so what I'm trying to harp upon in this is that it is not a very singular aspect that will define the battery prices going forward. But all these factors put together, along with the consumer demand, along with the increase in the manufacturing capacities of battery, along with the stabilization of lithium carbonate mining prices and other things. So it's a macroeconomic effect that's going to happen. Yes, there has been a huge blip. You can partially blame it on COVID also, although it's on the verge of, let's say, reduction or stabilization on that front. But last October, November, so there was COVID restrictions in various countries, various regions. So yes, there has been a major blip, but what I see is that going forward, there is going to be no shortage of requirement or no shortage of deployment in battery storage across the globe, and stability will come in the next 3 to 6 months. Moving on to the next slide. Rob, this one's for you on the right-hand side. So until I probably tell my colleagues about the first 3 points, you can go through the 4th point. Yeah, so here I come is that what we have done till now in Africa is that we have deployed 3 projects in Nigeria. They are for a government entity called REA. And the 3 projects are solar plus storage plus DG. So one of them is a 24 megawatt hour, the other one is an 8.64 megawatt hour, and the third one is a 5.1 megawatt hour. All 3 have been connected, and they've been operating for more than 3 years now, approximately 3 years now. And these are totally off grid. So they run basically only on the DG, the solar, and the batteries. And fundamentally, it has provided electricity to all these universities and reduced their, diesel consumption. The second project which we commissioned, that's Mali, has been commissioned probably just a month ago. So this is specifically for a gold mine in Mali. And the developer who went ahead with this was called Vivo Energy. Fundamentally, what happened was the mine already had 6 running DGs. So Vivo Energy, they wanted to get into a greener, production electricity. They are a developer. So we have come out putting up a 2.58 megawatt hour battery with a 3.5 megawatt peak solar and integrating it with the existing 6 DGs. And with this, we've been able to approximately reduce the, or increase the renewable penetration to approximately 45% of the entire load requirement of the client. The third one, it is under contract right now. Basically, we have not yet closed it. So it is going to take some time for us to commission that. And probably we will be giving you the update in the next kind of couple of months of interactions that we might have. Now, just to give a rough idea to the entire team that's around, if a mine or if a requirement comes across as a 1 megawatt load for 24 hours, and the basic requirement is, let us probably try and see if we can negate 50% of the load with renewable penetration. So what exactly we will have to do is we will have to size the solar and battery accordingly. If you see that, what I have done, it's a very rough thumb rule based calculation that I've done. It is not a detailed analysis. Obviously, we can optimize it further on depending on the load requirements, depending on the actual site location, the generation at that point, with the modules, with bifacial, with tracker, and all these things. I mean, with string, central inverters kind of thing. So yeah. So what exactly happens is if we have a 1 megawatt load for 24 hours, obviously we need 24 megawatt hour of load. Now, fundamentally, if we have to do 50% of that, we will need to give the load 12 megawatt hour from our renewable sources. So the renewable sources here are solar and BESS, solar and BESS. So fundamentally, if we have a 2.5 to 3 megawatt, we'll be able to generate approximately 14 megawatt of load. Now, from that 14, all 14 cannot go to the grid at the same time because it's a 1 megawatt load. At some point of time, solar is going to generate 1.5 to 3 megawatt, depending on the size, depending on the irradiation and other things. So the excess generation will be captured into the battery, and that will be stored and will be used to provide power whenever and as and ever required to the load, depending on the EMS, depending on how we prioritize, whether DG has to be prioritized 1, BESS second, solar third, DG 1, solar second, BESS third, depending on that kind of thing, we can prioritize. So if you see the configuration that is needed for catering to a 1 megawatt continuous load will be approximately roughly around 2.5 to 3 megawatt of solar and approximately 5 to 6 megawatt hour of BESS. In terms of capex, if you look at it, as Rob was mentioning previously, a roughly 100 USD cents or 0.8 to 1 USD per kilowatt peak, and this is around 400 USD per kilowatt hour. The total capex for solar approximately turns out to be in the region of 3 million, and for battery turns out to be in the region of 2.4 million, with a total approximate capex coming to around 5.4 million. Now, the ROI or the IRR for this depends on obviously what tariff you're getting, at what rate of interest you're taking the loan. I mean, what kind of equity you're putting into it, and a lot of other factors. So generally, we have seen that in Africa, the ROI differs from 4 to 6 years, and we are able to meet these kind of requirements very easily.
Perhaps a comment to add to this is,
yeah.
I mean, my understanding of this case study is you're offsetting either on-site diesel or a combination of on-site diesel or utility prices in Africa, which are intermittent.
It's utility prices, yeah, mainly diesel, because if a mine kind of thing, there would ideally not have a grid there. It would be very remote location. So offsetting diesel, we would have a good ROI. Offsetting utility or grid, probably will have a different case study altogether, depending on how much power we have, what time we have that power, and what will be the rate of that power. So we would have to do a separate study on that front.
Yeah, agreed. And I think we've been making a lot of work for various clients, and I think to offset megaflex tariffs in the peak times, I think are difficult at the moment with lithium-ion prices where they are in demand. We believe perhaps offsetting mini flex or municipal tariffs in the peak times are going to be there, and we think are already viable. We were hoping that battery prices coming down and mega flex going up, we would have had to be at the crossover point there this year.
Right.
But I think with macroeconomic conditions, perhaps it's been kicked down the line. But I think for most of our smaller users on more expensive grid-connected tariffs, specifically in South Africa, I believe that BESS for peak shaving is definitely already viable. Yeah.
Yes, very true. Very true. It's peak shaving is viable probably across the globe right now. I mean, if we are able to do the right sizing.
Agreed. Cool. Okay. Next slide, if you're done.
Moving
Yeah.
on to the next slide, I think this would be one of my last slides. Basically, this just gives you a fair idea of what exactly we did in the Nampala gold mines. I've already detailed it out in a decent manner. I'll be sharing the slides. So obviously, you will get a fair more idea of, we using bifacial modules, we using trackers, and we using trackers in such a way that it can be moved and fixed into another plant after 5 years because the PPA was for 5 years. So those kind of EPC experiences we've used across what we've done across our lifetime. So helping the client achieve what he wants at the right price, at the right time, at the right cost. And yes, as mentioned previously and now again, we can do the entire turnkey EPC from solar, pure solar, pure storage, or solar plus storage co-located as you call it. And obviously, we are capable of doing the entire thing across. That's it from my end. I hope I'm not put people to sleep. Sorry.
No, I think that was good, Shyam. Thank you. So I have a few prepared questions. I see we have one question in the chat box, so please other people add to that, and we'll go through it there. But my first prepared question is, and this is crystal ball gazing, is when do we believe that those non-lithium ion or supported flow technologies will be implemented? And I'm conscious that it depends on both commercial viability and as well as EPC's willingness to take the technology risk. But if we had to put you on the spot and you could disclaim for 10 minutes and then give us a date, do you have a feel for when we might have that crossover point where both you're willing to take the technology risk as an EPC and where we might see it being commercially viable for, let's call it grid connected clients? So, people paying 6 or 7 US cents perhaps in today's money.
I totally understand that. I mean, when I was explaining the slide, as I mentioned to you, I mean, and you also mentioned to me a couple of times during the question right now that commercial viability. So fundamentally, that is the primary requirement for anybody is the commercial viability. Now, when does it have commercial viability? Obviously, if it has been tried and tested, and obviously, if it can be manufactured at such a level that it makes commercially viable solutions. So the trials and testings are already ongoing for flow batteries. If I'm not wrong, it has a fantastic future going forward. The reason I'll tell you is that the current requirements of 1 to 4 hours of storage are going to change very slowly, because moving forward, the renewable penetration into the grid is going to increase further exponentially across the globe. So obviously, rather than having only 4 hours of storage, or rather than having only 4 hours of reliability, people will need more than 10 hours of reliability, or approximately 10 hours of reliability. That is where lithium-ion batteries will not be able to suffice at that point of time. So I will not be the right person to gauge or answer whether it will be flow batteries at that time or some other different kind of storage. But yes, looking at the current scenario, flow batteries are likely to get into it probably in the next short to medium term, let's say 5 to 7 years approximately.
Cool. Thank you. Then I guess the next
sorry.
No, please finish, Suran.
And these will generally start coming into countries and regions where the renewable penetration increases faster. So if you get my point, let's say like a country like UK, where approximately 35% of their grid is right now, getting renewable energy. I mean, the 35% of the entire load is being catered by renewable energy. The load and the fluctuations of demand are very, very, it's very, very tough to maintain it. That's why you have an entire separate market for BESS there. Similarly, in Australia, where there's a lot of renewable energy penetration happening. So these are the countries which will start off with flow batteries, and obviously it will flow into the other regions slow and steadily as and when it makes commercial sense in that region.
Cool. Thank you very much. My next question is, the South African president recently announced that 10-point plan on energy. planning, and within that, they plan to submit asking for bids to supply solar power and battery storage at Komati Majuba, and they're talking about 500 megawatts of capacity. And then in addition to that, the DMRE is to release a request for proposal for battery energy storage and systems later this year. So I guess the question is, Eskom's approach, is this the right one? And then the second one is, if you suddenly won a tender for 500 megawatts of capacity tomorrow, let's assume you were the winning tenderer, do you think we have the ability to actually implement that scale based on global demand and shortages in the timelines that I've mentioned?
So, Rob, just to give you a small heads up, 500 megawatt hour of battery fundamentally is not a very big size currently. Across the globe, USA, Europe, Australia, these are places, I mean, Latin America, these are places where we are bidding for projects in the region of, 200 by 400, 400 by 800, 400 by 1600. So a 500 megawatt hour of battery in a stipulated timeline of 18 months should not be a problem at all, even looking at the current scenario of shortages of battery, or the lead times being longer. If we have an 18-month timeline, the battery manufacturers are ramping it up, as I mentioned. Obviously, they will stabilize by the next 6 to 9 months or a year or so. But 500 is not a number that we need to worry about. I mean, anything that goes beyond 5 gigawatt or something, that is something that we need to worry about. So if a country is coming out with a bid where saying that I need 10 gigawatt hour of battery in the next 1 year, that's something that I'll worry about, because the global macroeconomic scenario does not support that kind of installations in such a short duration of time. But if you ask me personally, 500 megawatt hour should not be a problem going forward.
Cool, thank you.
And then I guess the second question by any chance?
Yeah, the second question was around, is this the right approach by Eskom that you've seen globally, or and you mentioned in Australia, IPPs are taking on these roles, whereas this looks more like an EPC type engagement?
Yeah. So again, Rob, this is fundamentally a very very difficult question to answer. Let me make it. There are regions and countries and across the globe, and every region and country works in a different manner. If you ask me personally, we cannot compare Australia to Africa. We cannot compare Africa to India. We cannot compare India to USA. I mean, every region, every country has its own way of looking at things. Now, fundamentally, let me just give you a brief idea. India is coming out with an IPP tender as well as an EPC tender for BESS. So it's a dual approach that they've taken. I mean, Australia, they come out with pure IPP tenders where it is co-located. In UK, it is pure BESS, no co-located right now. It's right next to the substations. So every region, every country has its own way of looking at things and own way of solving the problems that they're going to come up with the grid, with the renewable penetration into the grid. So there is no specific, a single point direction that you can, point out and say that this is exactly how it will work across the globe. I mean, if that was the case, then everybody would be copying the first guy who's done it the right way. So fundamentally, I would say that it is up to the government, up to each country to determine what kind of support that kind of technology or that generation or that entire system will need to push it further into acceptance in that region. I mean, it is for the government to decide, and obviously the government also sometimes makes mistakes. I mean, there is no right and wrong specifically right now. So I would say that it is not a wrong approach. I mean, I would not say whether it is a right approach. I'm not the right guy to actually answer the question unless it is executed. So
thank you. And then my last question, and I thank you for sending the questions through. Maybe we could just work through them on the day. Is in REAP round 6, the RFP is actually requesting the provision of ancillary services in South Africa, similar to the medium-term risk mitigation, which was a storage or thermal. I know you're supporting a number of projects in REAP. Are you seeing IPPs, without giving away too much, focusing on this as an area? And then do you also believe for private sector who also have large procurement programs that and provision of ancillary services would help with both the revenue model as well as obviously supporting the grid? And are we seeing that approach elsewhere in the world?
Fantastic. So I'll answer the second part of your question. And probably if Raj is still around, I'll let him answer the first part. So the second part is that, yes, it's a very good move that the government has come out with. Across the globe, in Europe, in UK, in USA, ancillary services, the revenue models, the stacking of revenue, all these have helped IPPs get into the market, have helped the penetration of BESS into the systems. So what South Africa has done right now is fundamentally a very good initiative that they've taken, which is only going to increase the entire market penetration of BESS and obviously support the renewable penetration into the grid. And for the first question, if Raj is still around, Raj, I would like you to take that.
Yeah, thanks. So yes, ancillary services, these are the new initiative, I would say, taken by government. See, it's more like a, as indicated by Sriram, right? It's a progressive or emerging technologies. And as the penetration goes, uh, each and every government or country will come out with their own set of things. But especially when it comes to ancillary services, this is a good initiative taken by the government, and in fact, it will have a good substantial impact in next 2 to 3 years time, because as the government or president has also announced the deployment of new renewable energy, as well as free of the entire IPP things, that will help us in terms of better penetration and growing of the renewable energy.
But I guess if I can ask a direct question, are we seeing IPPs in bid window 6 actually put forward strong technical solutions to achieve this, or is it just lip service? Because I know it's a nice to have as opposed to a requirement at the moment.
At the moment, it's every IPP is considering as a requirement, to be honest with you. But see, it goes hand in hand, right? One is like, once you prove the requirement is right, then eventually people will adopt it automatically from a future perspective. So no one going to immediately say yes and start deploying it. Definitely, it will increase some sort of cost, budget, and all those things. It will have impact on tariff. So all these things will happen. But at some point of time, we need to take a decision, move forward, and that's what IPP will do it now.
Thank you very much. Thank you very much for that. So Shriram, I assume you can see the chat box. I don't know if you'd mind just working through, read the question.
Perfect. I will do that. I will do that.
And then if you have require specific clarity, if you can just ask the person who asked the question just to clarify, and we can work that through for the last 15 minutes of the call. And please continue to add questions into the box and work on a first.
Can I start from the first one?
Perfect. Let's go on first mover. Yeah, first question gets first answered. Thank you, Lo.
Perfect. Perfect. So it's from Swartz. So yeah, so 1% of the initial capital cost for lithium ion, I mean the annual operational cost. So there are two aspects to it. If you need extended warranties, the battery manufacturers generally give a 3-year warranty and the inverter manufacturers give a 5-year warranty. Once that is done, obviously there will be a yearly extension of battery warranties. That yearly extension itself will cost you 1%. So over and above that, if there's some monitoring to do, and this is only for the battery, I'm trying to tell you. If you look at the entire amount of money that will be required, will be close to 2%. So this is after 3 years, to be very precise. The first 3 years will be very less because there will be no extended warranties required for battery or PCS. The PCS is after 5 years and the battery is after 3 years. I hope I've answered.
The next one, to give us a thumbs up or not, or we want to unpack
that's perfect. That's very helpful. Thank you very much.
Cool, thanks, Lo. And then Jargon.
Perfect. The next one. So the depth of discharge, only 80%. So this depends. I mean, there are manufacturers who give up to 96% and 98% also. So it will depend on the lithium ion battery and the manufacturer you choose. It is not 80% standard across every manufacturer. So you go to tier 1 good suppliers, which are probably a little bit on the premium side, you might get up to 95 to 97%, but it will also depend on your C rating and number of cycles. So if you have a higher C rating, then obviously your DOD goes down. If you have a lower C rating, obviously your DOD can go up to 96, 98%. So generally for a 1 cycle application, for a 4-hour or a 2-hour application, you can get up to 95% to 97%. Hope that's done.
And just to answer the question specifically, and try to jump in here, if they have a lower cycle efficiency, do they need to probably oversize to get to the same megawatt hours?
Yes,
And I assume
yes,
that would be a
yes.
yes.
And not only
Yeah.
that, I mean, not only the DOD, I mean, there will be many other losses. There'll be DC losses, AC losses, transformer losses, all those things put together, auxiliary consumptions, and whether the size is required for the beginning of life or the end of life. Yes, generally BSS systems are oversized. On a standard basis, up to 10 to 15%, depending on beginning of life, one cycle kind of thing. If the DOD is 80% only, then obviously it will be oversized to a much higher requirement.
Does that answer your question or any clarity?
Yeah, I just wanted to know, so what do I pay for if I need 1 megawatt hour usable storage? Do I pay
Right.
for 1.2 megawatt hours, or do I still pay for 1 megawatt hour at a rate of $200 to $300 per kilowatt hour?
No, it's about installed capacity. I mean, usable capacity can obviously differ because depending on your usage, depending on your requirement. So installed capacity is what I was trying to mention, and 200 to 300 is a huge wide range. I mean, it is just to give you a thumb rule kind of idea of where exactly we stand right now. So fundamentally, if you go to any supplier and ask them that you need 1 megawatt hour usable, whether they put 1.2, 1.3, 1.4, they won't even tell you that. But we as an EPC, obviously, we can tell you that. So they wouldn't even let you know how much they've installed, but they'll give you a final number, which you will feel is for that 1 megawatt hour of usable capacity at beginning of life.
Okay, thank you.
Yeah.
I mean, we have found that that sort of question is very site specific, generation specific, what do you have to charge the battery and vice versa. Thank you. Next question from Barent.
Yeah. So total capex from battery to AC side of inverter. I mean, you're talking about the entire BOP side, if I'm not wrong, Barent? Other than the battery
Yeah, so
container.
I mean, if you talk from AC side, so you basically charge and discharge. So if I'm basically the usable power, cannot really use the DC side. So what will be the capital cost? Or is it $200 to $300 only for the battery, and then you need to add the inverter and all the other stuff?
Yes, yes. So we will have to. So let me give you a brief heads up. The battery, obviously, there will be a DC. Do you want me to show the slide again? My intel once again.
Yeah, maybe that will help. Agreed.
Yeah.
Yeah, here you go. So what you said is this is the container that we have. Right?
Yeah.
We have a DC combiner after that. We will have the bidirectional inverter after that, or a PCS. Then obviously the transformer, the AC cable and the MV panel, all this has to be added depending on the C rating. Now, fundamentally what happens is if you're looking for a 1C application, what happens in a 1C application is if you are doing a 1 megawatt hour plant, you're doing a 1 megawatt PCS also. That is the DC to AC ratio is 1. Then obviously the inverter cost increases. If you have a 4-hour system, so for a 1 megawatt hour battery, you just have a 250 kilowatt AC side. So, it will not be a very standard application like you can probably put it across, but to give you a very, very rough and brief idea and, and not stepping it up to some 275 kV or 132 kV levels, if we are trying to terminate it at 34.5 kV level or 33 kV levels, the approximate cost, including civil installations and commissioning, testing, and all these put together, will be in the region of, let's say, anywhere between $75 to $110 per kilowatt hour.
But that's now on top of the 200 to 300, or is that?
Yes, on top of the 200 to 300. Yes.
So the 2 to 300 is basically just the battery.
Just the battery. Yes, yes.
Straight to the DC combiner or something like that. Maybe there somewhere there. The rest is in the. You say another $150.
Yeah, if you get a container, you will get the DC combiner with it. But after that, you won't get anything. There are some we give you with the PCS also. Those are some technologies which give you with the PCS also. Then obviously those are close to the 300 mark. You get the point of me giving that is that some give you only the battery containers. Then the entire thing after this has to be built by us. Some give up to here as a single product. Then only this part has to be built up.
How much is that last part you said? Sorry, I missed that.
I didn't get you. Can you repeat your question?
What's the cost for the last part? You said, is it $75 to $150?
$110. Yeah, 75 to 110 approximately.
75 to 110. Okay.
From here to here. I mean, these are all thumb rule estimates. I mean, unless we actually get into the sizing and see what kind of PCS, I mean, what is the C rating and what kind of cable. It's okay. Yeah, I mean, for this.
Yeah, no, I understand. It depends on the secondary voltage and that will change it. Yeah. Okay.
Cool.
And then just
maybe
around trip efficiency, basically the efficiency from AC to AC, or I'm not sure if you do it from DC to DC, the round trip efficiency.
Yeah, so I'll give you a rough idea. The efficiency from AC to AC, that is, if you're going to take power from the grid, charge the batteries and discharge the entire power back into the grid, approximate efficiency is between 85 to 86%. And the DC to DC.
The point
is that sort of constant over many of the suppliers, or is it very supplier specific?
It would vary a little bit. It would vary a little bit, but fundamentally what happens is only the first question, if you remember the DOD, that is the only one that hits it. Other than that, all the other factors remain the same for most of the, because it's again the DC combiner boxes, the DC cables, the PCS, the transformers, all those losses remain the same going forward. And the DC to DC efficiency is close to 92, 93% approximately. I mean, these are all rough estimates depending on what we've done or what I've done.
I mean, I think that what we've realized more and more as we go out on these sort of tenders on storage is, like PV, you need to be quite specific in your requirements. Battery, you need to even be more specific and explain why you need it. Just saying I need a battery solution is difficult, because we see significant ranges of pricing just on the PV side, but on the battery side recently, on a recent RFI, it was apples and lemons and everything else in between, because the scope wasn't probably defined enough. Sweet.
Yeah.
Cool.
Sorry,
the next one.
My network fell off.
No problem. Thanks, Byron. Battery, I don't know if your question was actually answered through Shriram's last explanation, or do you want to specify?
Yes, thank you.
Okay. Great. I see there's no more questions. I don't know if anyone on the call wanted to make some comments. Otherwise, I think we can finish this and go back to the other world of Teams. But I see Mark has a comment, so thanks, Mark. Please jump in.
Just a quick question on firefighting systems. Is it traditionally a firefighting system, a water-based firefighting system specified for these BESS installations in your experience, and a halon system for the electronics, or do they simply use NFPA distances for spacing between units of property to prevent fire propagation? Used as a method, because installing a water system is not the easiest thing in the world.
Yeah,
sorry, I didn't see your question. Apologies, I didn't scroll down.
Well, that's your problem there, Rob. I mean, attention to detail has never been one of your strong suits, my friend.
That's why we have
Just kidding.
modules. Thank you.
Just kidding, boss. Just kidding, boss.
Thank you. Cool. Shriram, can you answer that question?
So yeah, so firefighting specifically in batteries, yes, there are liquid cooled, I'm not talking about the cooling, sorry. So the firefighting, yes, as you mentioned, there are different types. I will not probably be the right guy to answer to you, because you've gone into a little more detail than I would have probably know. I can probably, if you can just mail me that question, I can get you answered by the technical guy, and probably, I'm sorry about that.
I'll send it off with Mark in messaging, and you can come back with a question. Thank you, Shriram. And then I think there was one more from.
Just one question.
Sorry, just Byron. Sorry, we just have one more question from Dragon, and then you can come in at the end if that's okay.
Hi, thanks. It's not a question. It's just a suggestion for this slide in front of us. The bottom row, if you put the arrow the other way around, then it will show that it's bidirectional, and it would have this logic of charging battery and discharging.
I'll do that. Thank you. I'll make a double arrow on that side. Yeah.
Thank you. Byron, do you have a question?
So I assume these batteries, if you make them nice containerized, it looks like a really modular thing. You can just load it onto a truck and take it anywhere. how long does it take? Is it, say for instance, we order a 5 megawatt unit or 20 megawatt of these containers, and how much megawatts do we get into a container, just to visualize the space a little bit? And just the lead time generally.
Okay, so there are 3-4 into it. So approximately a 40-foot container would have anything in the region of 2.5 to 4 megawatt hour. So if you're talking about a 20 megawatt hour system, let's say 4 to 6 containers. Probably 5 to 7 containers, sorry. Around 3 to 5.
That's a normal and that's a 40-foot container.
That's a 40-foot container, yes. Fundamentally, what exactly happens is that, but the moment you load it into a 40-foot container, you will have to ensure that it turns out to be much more than 24 tons. So 24 and 27 metric tons. So probably you will need special cranes and special equipment to, lift it up, place it, and it turns out to be in the 30s. The weight turns out to be in the 30s.
And the lead time?
See, under current scenario, it's close to 10 months to 12 months. I expect it to go up to 14 months in the next 1 or 2 months. But post that, it is likely to reduce.
That's FOB, or is it delivered in South Africa?
So the manufacturing lead times are close to 9 to 10 months. Obviously, you need a couple of months more for the delivery to reach any place. I mean, depending on minimum 30 days to maximum 60 days of transit time.
Okay, great, thanks.
And then 6 months to get out of Durban Port, Barrett. Yeah.
Yeah, you have to carry it out.
Wow.
Exactly.
I just told you all it's much heavier than the normal container also.
You haven't seen how big Barrett is. Sure. No, but cool. Thank you very much. We're digressing. If there are no other questions or comments, I see no hands or comments. Shriram, I don't know if you have any more comments, but
No, I mean, nothing from my side. I just hope that it was helpful, and thank you for listening to me patiently, and hope it was useful to all of you. Thank you.
Brilliant. No, thank you very much. So just to recap, we will send a recording plus the PDF version of these slides and a little roundup in a week or two. And thank you very much, everyone. We will also be having another webinar next week, Thursday. So I hope you can attend and join us. Thank you very much for everyone's time. Have a good afternoon.
Thanks all. Very nice.
Thank you all. Thank you.
Thank you.
Thank you.
Bye.
Bye.
Thank you. Thank you. Goodbye. Bye.
Bye.